What if I told you that right now, as you're watching this video, you're not actually touching anything? That the chair you're sitting on, the phone in your hand, even your own body, none of it is truly solid. In fact, what if everything you think of as matter, every atom, every particle, every piece of physical reality, is actually just light moving so slowly that it got trapped and frozen into what we call mass? Here's the mind-blowing part. Einstein proved this over a century ago with the most famous equation in history, E equals mc squared. But what most people don't understand is what that equation actually means. It's not just some abstract mathematical relationship. It's telling us something profound about the nature of reality itself. Energy and mass are the same thing. Light and matter are the same thing. The only difference is speed. Think about that for a second. The atoms making up your body right now, the carbon, the oxygen, the hydrogen, all of it is just energy that's been slowed down and trapped in a particular configuration. You are literally made of frozen light. Not metaphorically, not poetically, literally. And here's what's going to blow your mind even more. Physicists have actually done this in laboratories. They've taken pure light photons with no mass at all and converted them directly into matter, into electrons and their antimatter counterparts, positrons. They've watched light become solid. They've proven that matter really is just trapped light. By the end of this video, you're going to understand exactly how this works, why it's true, and what it means for everything you thought you knew about reality. We're going to explore one of the deepest mysteries in all of physics. And I promise you, your mind will never think about the physical world the same way again. But before we dive in, do me a favor, hit that like button and subscribe to the channel. And I'm genuinely curious. Drop a comment telling me what country you're watching from and what time it is where you are. I love seeing how far these ideas spread across the globe. Are you watching this at midnight in Brazil? During your morning coffee in Japan? Let me know. All right, let's start with the foundation. To understand how matter is trapped light, we first need to understand what light actually is. And I'm warning you right now, what you learned in school was probably incomplete at best and misleading at worst. For most of human history, people had absolutely no idea what light was. The ancient Greeks thought it was something that shot out of your eyes and bounced off objects. Seriously, they thought vision worked like reverse headlights. It wasn't until around the year 1000 that the brilliant Arab scientist Ibn al-Haytham proved that light actually travels from objects into our eyes, not the other way around. That was the first major breakthrough in understanding light. But the real revolution started in the 1600s. Isaac Newton thought light was made of tiny particles he called corpuscles. Meanwhile, a Dutch scientist named Christian Huygens argued that light was a wave, like ripples on a pond. For over 200 years, physicists fought about this. Team particle versus team wave. And here's the twist. They were both right, and they were both wrong. In the early 1900s, Albert Einstein made a discovery that would eventually win him the Nobel Prize. He was studying something called the photoelectric effect, the way light can knock electrons out of metal. And what he found was shocking. Light behaves like it's made of discrete packets of energy. He called them quanta. We now call them photons. Light, it turns out, is both a wave and a particle at the same time. This was the birth of quantum mechanics, and it shattered everything physicists thought they knew about reality. Think of it like this. Imagine you're at the ocean, watching waves crash on the beach. The waves are clearly waves. They have peaks and troughs. They spread out. They interfere with each other. But now imagine that when those waves hit the sand, they suddenly become individual droplets of water, each one carrying a specific amount of energy. That's sort of what light does. It travels like a wave, but interacts like a particle. It's one of the strangest things in all of nature. Now here's where it gets interesting. These photons, these particles of light, have zero mass. They're pure energy, moving at the fastest speed possible in our universe, about 300 million meters per second. At that speed, from the photon's perspective, time doesn't even exist. A photon emitted from a star a billion light years away experiences no time between leaving that star and hitting your eye. From its point of view, the journey is instantaneous. But photons do carry energy. The amount depends on their wavelength. Blue light photons carry more energy than red light photons, for example. And here's the crucial part. According to Einstein's theory of relativity, energy has mass equivalence. Not actual mass, but what we call relativistic mass. When a photon interacts with matter, it can transfer its energy, and that energy can be converted into actual mass. This is where Einstein's famous equation comes in. E equals mc squared. Energy equals mass times the speed of light squared. What this equation is really telling us is that energy and mass are interchangeable. They're two forms of the same thing. Mass is just a very concentrated form of energy, and the conversion rate between them is the speed of light squared, which is an absolutely enormous number. Let me put this in perspective. The speed of light is about 300 million meters per second. Square that, multiply it by itself, and you get 90 quadrillion. That means 1 kilogram of mass is equivalent to 90 quadrillion joules of energy. That's roughly the energy of 20 million tons of TNT. The atomic bomb dropped on Hiroshima converted less than 1 gram of mass into energy, and look at the devastation it caused. So when we say matter is trapped light, what we're really saying is that matter is trapped energy. And since light is pure energy in motion, matter is what you get when you somehow slow that energy down and lock it into a stable configuration. But how does that actually happen? How do you trap light and turn it into matter? Here's what will blow your mind. It happens through a process called pair production, and we've actually observed it in laboratories. When a photon, a massless particle of light, has enough energy and interacts with a strong electromagnetic field, it can spontaneously convert into a particle and its antimatter partner. The most common example is when a high-energy gamma-ray photon converts into an electron and a positron. This was first predicted by Paul Dirac in 1928. Dirac was trying to develop a quantum mechanical equation that was consistent with special relativity, and his mathematics kept spitting out strange solutions that suggested particles with negative energy. At first, he thought this was just a mathematical quirk, something that didn't represent physical reality. But then he realized these negative energy solutions were predicting the existence of antimatter. In 1932, American physicist Carl Anderson discovered the positron, the antimatter counterpart of the electron in cosmic ray experiments. It was exactly what Dirac had predicted. And when researchers studied these positrons, they found something remarkable. They could create electron-positron pairs directly from gamma-ray photons under the right conditions. Light was literally becoming matter before their eyes. Think of it like this. Imagine you're watching a perfectly calm pool of water. Suddenly, a wave appears, but not a normal wave. This wave splits into two whirlpools, one spinning clockwise and one spinning counterclockwise, both perfectly balanced. That's sort of what happens in pair production. A photon, a wave of electromagnetic energy, splits into two particles with opposite properties, an electron with negative charge and a positron with positive charge. The wave has become matter. But here's the catch. This only works with very high energy photons. A visible light photon doesn't have nearly enough energy to create an electron-positron pair. You need gamma rays photons with energies of at least 1.02 million electron volts. That's about 1 million times more energetic than visible light photons. This is why you don't see your flashlight spontaneously creating matter when you turn it on. Now, you might be thinking, okay, so light can become matter, but that's just one type of particle. What about all the other stuff? What about protons and neutrons, the particles that make up atomic nuclei? What about quarks? Are those made of trapped light too? The answer is yes, but in a much stranger way than you might expect. And this is where we need to talk about one of the most bizarre and beautiful theories in all of physics: quantum chromodynamics, or QCD for short. This is the theory that explains how quarks, the fundamental particles that make up protons and neutrons, are held together. And when you understand QCD, you'll see that even these particles are ultimately just energy configurations, frozen light in a very real sense. Here's where things get wild. Protons and neutrons are made of quarks, 3 quarks each, held together by particles called gluons. Now, you'd think that if you add up the mass of the 3 quarks inside a proton, you'd get the mass of the proton, right? Wrong. Dead wrong. The 3 quarks inside a proton account for only about 1% of the proton's mass. 1%. So where's the other 99% coming from? It's coming from the energy of the gluon field that holds the quarks together. The gluons themselves are massless. They're like photons in that respect. But the energy they carry, the energy of the strong nuclear force binding the quarks together, that energy has mass equivalence according to E equals mc squared. Almost all of your mass, almost all of the mass of ordinary matter in the universe, comes from the kinetic energy and field energy of massless particles moving around inside protons and neutrons. Let that sink in. You think you're made of solid stuff, but you're actually made of energy fields. 99% of your mass is literally the energy of massless particles zipping around at nearly the speed of light inside atomic nuclei. You're not just made of trapped light in some poetic sense. You're actually literally made of trapped energy from massless quantum fields. This was worked out in the 1970s by physicists like David Gross, Frank Wilczek, and David Pulitzer, who won the Nobel Prize in 2004 for their work on quantum chromodynamics. They showed that the strong force, the force that holds quarks together, has this bizarre property where it gets stronger as you try to pull quarks apart, like a spring that gets stiffer the more you stretch it. This is called asymptotic freedom, and it's why you can never isolate a single quark. Think of it like this. Imagine trying to pull apart 2 magnets connected by a rubber band that gets stronger the more you stretch it. Eventually, you put in so much energy stretching that rubber band that the energy itself creates 2 new magnets. And now you have 2 pairs of magnets instead of separated magnets. That's what happens with quarks. Try to pull them apart, and you just create new quark-antiquark pairs from the energy you put in. So here's where we are so far. We've established that photons, pure light, can directly convert into matter through pair production. We've shown that most of the mass of ordinary matter comes from the energy of massless gluons. But there's still one piece of the puzzle we haven't addressed. What about the quarks themselves? What about electrons? These particles do have what we call rest mass that exists even when they're not moving. Where does that come from? And this is where we encounter one of the deepest mysteries in modern physics, and one of the most recent major breakthroughs, the Higgs field. In 2012, physicists at CERN in Switzerland announced they discovered the Higgs boson, a discovery that won the Nobel Prize the very next year for Peter Higgs and Francois Englert, who had predicted it back in 1964. And what the Higgs field does is absolutely mind-blowing. The Higgs field is a quantum field that permeates all of space every cubic centimeter of the universe, including the space between your atoms and inside your atoms. And here's the crucial part. Fundamental particles get their rest mass by interacting with the Higgs field. Particles that interact strongly with the Higgs field have more mass. Particles that don't interact with it at all, like photons, have 0 mass. Think of it like this. Imagine you're trying to run through an empty room versus running through a room filled with molasses. In the empty room, you can accelerate quickly. You have low effective mass. In the molasses room, it's much harder to accelerate. You have high effective mass. The Higgs field is like molasses that fills all of space, and different particles experience different amounts of drag from this field. Electrons experience some drag, so they have a small mass. Quarks experience more drag, so they have more mass. Photons don't experience any drag at all, so they're massless and always travel at the speed of light. But here's the kicker. The Higgs field is itself an energy field. It's not made of matter. It's a field, like an electromagnetic field, that has a certain energy density throughout space. And particles acquire mass by constantly interacting with this field, by constantly exchanging virtual Higgs bosons. So even the rest mass of fundamental particles is ultimately coming from energy interactions with a field that permeates space. Are you starting to see the picture? At every level, from pair production creating electrons and positrons, to gluon field energy creating most of the mass of protons and neutrons, to the Higgs field giving particles their rest mass matter, is ultimately just different configurations of energy. Different ways that energy can be trapped, bound, and frozen into what we perceive as solid, tangible stuff. Now let me show you something that's going to make this even more concrete. In 2017, researchers at the Brookhaven National Laboratory in New York actually created matter from pure light, or more accurately, from collisions of light-like particles. They smashed together heavy ions at such high energies that their electromagnetic fields interacted, and those electromagnetic field interactions created electrons and positrons. But even more impressive, in a paper published in 2021, physicists outlined a detailed plan for creating matter from light using just lasers. The idea is to use extremely powerful lasers to create such intense electromagnetic fields that photon-photon collisions can produce matter particles directly. This experiment, called a photon-photon collider, hasn't been done yet because we don't quite have powerful enough lasers, but the physics is solid. Within the next decade or two, we'll probably be able to shine light at light and watch matter emerge from nothing but pure electromagnetic energy. Think about that. We're on the verge of being able to create matter from light in a controlled way, in a laboratory, using technology we built. We're about to prove, beyond any shadow of doubt, that matter really is just frozen light. But let's go deeper, because there's another layer to this that's even more profound. We've talked about how energy becomes matter, but we haven't really addressed the fundamental question. What is energy? What is this stuff that can be light or matter, depending on its configuration? Here's where physics truly strange. According to quantum field theory, the most successful theory in all of physics, the theory that's been confirmed to better than 10 decimal places in some experiments, what we call particles aren't really particles at all. They're excitations in quantum fields. The entire universe is filled with fields: an electron field, a quark field, a photon field, a Higgs field, and so on. What we perceive as particles are just localized vibrations in these fields. Imagine the surface of a pond. The water itself is like a field. It exists everywhere on the pond surface. Now imagine you drop a pebble in. A wave spreads out a localized disturbance in the water. That wave is like a particle. It has energy, it moves, it can interact with other waves. But it's not a separate thing from the water. It is the water, just in a particular state of excitation. That's what particles are in quantum field theory. An electron is a localized excitation in the electron field. A photon is a localized excitation in the electromagnetic field. These excitations can move around, interact, be created, and destroyed. But they're all ultimately just different vibration patterns and fields that permeate all of space. So when we say matter is trapped light, what we're really saying is this: the excitations in matter fields and the excitations in the electromagnetic field are intimately connected. They can convert into each other. They're different vibrational modes of the quantum fields that make up reality. Matter and light are like different notes played by the same cosmic instrument. This brings us to one of the most beautiful and profound ideas in all of theoretical physics: unification. For over a century now, physicists have been trying to unify all the forces and all the particles into one coherent framework, and we've made incredible progress. In the 1860s, James Clerk Maxwell unified electricity and magnetism into electromagnetism, showing they were two aspects of the same force. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg unified electromagnetism with the weak nuclear force into the electroweak force. They showed that at high enough energies, these two forces are actually the same thing. This earned them the Nobel Prize in 1979. The dream now is to unify all the forces, including gravity, and all the particles into one ultimate theory. String theory is one attempt to do this. The idea is that all particles are actually tiny vibrating strings, and different vibration patterns produce different particles. An electron is a string vibrating one way. A photon is a string vibrating another way. A quark is a string vibrating yet another way. If string theory is correct, and that's still a big if, then matter and light really are exactly the same thing at the deepest level. They're all just different vibration modes of fundamental strings. Matter is literally trapped vibrations, and light is vibrations that got free. But even if string theory turns out to be wrong, the core insight remains. Matter and energy are interchangeable. Light can become matter. Matter can become light. They're two sides of the same coin, two aspects of the same underlying reality. Now here's a question that might be bothering you. If matter is just trapped light, just frozen energy, why does it feel solid? Why can't your hand pass through a table? If it's all just vibrations and fields, why does it seem so concrete and substantial? The answer has to do with something called the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. This principle states that no two fermions particles, like electrons and quarks, can occupy the same quantum state at the same time. This is why matter is solid. This is why you can't put your hand through a table. When you try to push your hand through a table, what's really happening is the electrons in your hand are trying to occupy the same space as the electrons in the table. But the Pauli exclusion principle forbids this. The electrons repel each other, not because of electromagnetic forces alone, but because of this fundamental quantum mechanical rule. It's not really a force in the traditional sense. It's a statistical consequence of the quantum nature of particles. Think of it like this. Imagine a parking lot where each parking space can only hold one car. If every space is full, you can't park, there's simply no room. That's what happens when matter tries to pass through matter. The quantum states are full, and the Pauli exclusion principle says no more particles can fit. But here's the wild part. There's actually mostly empty space in matter. An atom is about 99.999999999% empty space. If you could remove all the empty space from the atoms in your body, you'd be smaller than a grain of sand. The reason you seem solid is entirely because of quantum mechanical effects like the Pauli exclusion principle and electromagnetic repulsion between electron clouds. So matter is trapped light, but the trapping is maintained by quantum mechanical rules that prevent different bits of trapped light from occupying the same space. It's like a cosmic game of musical chairs, except the music never stops, and there are very specific rules about who can sit where. Let me give you another mind-blowing perspective on this. You know how we said photons experience no time because they travel at the speed of light? Well, according to special relativity, as objects approach the speed of light, time slows down for them relative to stationary observers. At the speed of light, time stops completely. Now think about matter. Matter is essentially energy that's been slowed down from the speed of light. When you slow down from light speed, time starts flowing. Mass emerges. In a very real sense, matter exists in time because it's slower than light. Light exists outside of time, because it moves at the maximum speed. This means that the passage of time and the existence of matter are intimately connected. Matter is what happens when energy slows down enough that time can flow. You are experiencing time right now because you are made of slowed light. If you could speed up to the speed of light, if you could turn back into pure light, time would stop for you. The physicist John Wheeler, who was one of the great minds of 20th century physics and who coined the term black hole, once said something profound. Matter tells space-time how to curve, and space-time tells matter how to move. But we can go further. Matter is space-time. Or more accurately, matter is a particular configuration of energy momentum in space-time, and that configuration shapes the geometry of space-time itself. Einstein's general theory of relativity, published in 1915, showed that mass and energy curve space-time. The more concentrated the energy, the more space-time curves. In extreme cases, you get black holes regions where space-time is curved so severely that not even light can escape. But even ordinary matter curves space-time a tiny bit. The Earth's mass curves space-time around it, which is what we perceive as gravity. So here's the full picture. Energy vibrations in quantum fields are what we call particles. These vibrations can be massless, like photons, or massive, like electrons and quarks. Massive particles curve space-time around them. This curvature affects how all particles, both massive and massless, move through space. It's all one interconnected system, a cosmic dance of energy, matter, space, and time. And here's something that should absolutely blow your mind. This dance is reversible. Not only can light become matter, but matter can become light. This happens all the time in the universe. When a particle and its antiparticle meet, they annihilate, they completely convert back into pure energy, usually in the form of photons. This is what happens in certain types of medical imaging, like PET scans. PET stands for positron emission tomography. Radioactive tracers in your body emit positrons, which almost immediately collide with electrons in your tissue. When they meet, they annihilate, converting completely into gamma-ray photons. Those photons escape your body and are detected by the scanner. You're literally glowing with light produced by matter-antimatter annihilation. Every moment, inside your body, particles are being created and destroyed. Virtual particle-antiparticle pairs are constantly popping into existence from the quantum vacuum, existing for infinitesimally brief moments before annihilating back into pure energy. This is a consequence of Heisenberg's uncertainty principle. The quantum vacuum isn't actually empty. It's seething with energy, with potential, with brief flickers of matter emerging from and returning to the void. Think of reality like an ocean. The surface, the calm, visible part, is what we perceive as ordinary matter and light. But beneath the surface, there are constant currents, eddies, waves of energy flowing and churning. Occasionally, a wave crests high enough to break the surface, and we see it as a particle. Then it falls back into the ocean of energy. We are patterns in this ocean, temporary configurations of waves that have somehow achieved stability and complexity. Now let's talk about something even more mind-bending, the early universe. In the first moments after the Big Bang, the universe was so hot and dense that matter as we know it couldn't exist. There were no atoms, no nuclei, not even individual protons or neutrons. Instead, there was a seething soup of quarks, gluons, and other fundamental particles, all in thermal equilibrium with intense radiation. This state of matter is called a quark-gluon plasma, and we've actually recreated it in laboratories by colliding heavy ions at enormous energies. At the relativistic heavy ion collider at Brookhaven and at the Large Hadron Collider at CERN, physicists have briefly, for just a fraction of a second, produced conditions similar to those that existed microseconds after the Big Bang. In this quark-gluon plasma, matter and energy are barely distinguishable. Quarks and gluons are so energetic, so hot, that they move freely, not bound into protons and neutrons. The distinction between trapped energy, matter, and free energy, radiation, almost disappears. It's the primordial state of the universe, before energy froze into the matter we're familiar with. As the universe expanded and cooled, this plasma underwent phase transitions. First, quarks and gluons condensed into protons and neutrons. This happened when the universe was about 1 microsecond old. Then, when the universe was about 3 minutes old and had cooled to about 1 billion degrees, protons and neutrons started fusing into the first atomic nuclei, mostly hydrogen and helium. But it took much longer, about 380,000 years, for the universe to cool enough that electrons could bind to nuclei and form stable atoms. Before this moment, called recombination, the universe was opaque. Photons couldn't travel far before scattering off free electrons. After recombination, the universe became transparent and light could travel freely through space. That light is still traveling. It's called the cosmic microwave background radiation, and it's the oldest light in the universe. When you look at this radiation, which has been mapped in exquisite detail by satellites like WMAP and Planck, you're seeing light. That was last scattered 380,000 years after the Big Bang. You're looking back to the moment when matter and light finally separated, when trapped energy, atoms, and free energy, photons, became distinct. Think about that. The distinction between matter and light, between mass and energy, is something that emerged in the history of the universe. In the earliest moments, this distinction didn't exist. Matter is trapped light, not just in a physical sense, but in a historical sense. It's what happened when the universe cooled enough that energy could be frozen into stable configurations. And here's what's going to blow your mind about the future. This process is reversible on cosmic scales. In the far distant future, tens of trillions of years from now, the universe will have expanded so much and cooled so much that all the stars will have died out. Matter will slowly decay. Protons themselves are probably not stable on extremely long timescales, eventually decay into lighter particles and photons. In the ultimate heat death of the universe, all matter will have converted back into radiation. The temporary freezing of energy that we call matter will have melted. The universe will end as it began, as a sea of energy, with no frozen configurations, no trapped light, just photons spreading endlessly through ever-expanding space. But let's come back to the present, back to you, sitting here, made of atoms that are ultimately just configurations of energy. Because here's the personal connection I promised you. Understanding that you're made of trapped light changes everything about how you see yourself and your place in the universe. Every atom in your body, the calcium in your bones, the iron in your blood, the carbon that forms the backbone of every organic molecule, was forged in the heart of a star. Stars create heavier elements by fusion, mashing together lighter nuclei at tremendous temperatures and pressures. When massive stars explode as supernova, they scatter these elements into space. Those elements coalesce into new stars, into planets, into you. You are literally made of stardust. That's not just poetic language. That's the literal truth. The atoms in your left hand probably came from a different star than the atoms in your right hand. You're a temporary collection of matter that was forged in stellar furnaces billions of years ago. Matter that's been cycling through stars and planets and living things for billions of years. But it goes deeper. Those atoms, that stardust, is ultimately just trapped light, frozen energy from the Big Bang. The energy that makes up your body has existed since the beginning of the universe. It's been recycled countless times, taking countless forms, but it's the same energy. In a very real sense, you are the universe experiencing itself. You're a way that the cosmos has organized some of its energy into a configuration complex enough to be aware, to think, to wonder about its own nature. The energy in your neurons, firing right now as you process these words, is the same energy that existed in the quark-gluon plasma microseconds after the Big Bang, It's just taken a very long and complex journey to get here. This means something profound. You're not separate from the universe, looking at it from outside. You're not a ghost in a machine, some immaterial consciousness inhabiting a physical body. You are a pattern in the fabric of reality itself, a temporary organization of energy that has achieved self-awareness. When you look at the stars, you're looking at your origins. When you study physics, you're studying your own fundamental nature. And here's what this means for how you should think about yourself. Your boundaries are not as clear as you think. Where do you end and the rest of the universe begin? The air you breathe becomes part of you when oxygen molecules enter your bloodstream. The food you eat literally becomes your body. Those molecules are incorporated into your cells. Your cells are constantly dying and being replaced. Every few years, almost every atom in your body has been replaced. You're not a static object. You're a process, a pattern of energy flow that maintains a certain organization while constantly exchanging matter and energy with your environment. You're like a whirlpool in a river. The whirlpool has a persistent shape, an identity, but the water molecules making it up are constantly changing. The whirlpool isn't made of particular water molecules. It's made of a pattern, a flow. That's what you are. A pattern of energy flow, made of light that learned to trap itself in increasingly complex configurations until it became aware of its own existence. Now let me tell you about one of the most beautiful experiments in modern physics, one that really drives home how matter and light are interchangeable. The double-slit experiment, but done with electrons instead of photons. The classic double-slit experiment was first done with light. You shine light at a barrier with two slits in it, and on the other side, you see an interference pattern alternating bands of light and dark. This proves light is a wave, because only waves can interfere with themselves like that. The wave goes through both slits at once, and the two parts interfere on the other side. But here's where it gets weird. If you do the experiment with the light intensity turned down so low that only one photon goes through at a time, you still get the interference pattern. Each individual photon somehow interferes with itself, as if it went through both slits simultaneously. This is one of the central mysteries of quantum mechanics. Now, here's the mind-blowing part. You can do the exact same experiment with electrons. Fire electrons one at a time at a double slit, and they create the same interference pattern. Matter particles behave exactly like waves, just like light does. They interfere with themselves. Each electron seems to go through both slits at once. This experiment has been done with bigger and bigger objects. Not just electrons, but whole atoms, even molecules. In 2019, researchers in Vienna did the double-slit experiment with molecules made of up to 2,000 atoms. These are big, complex molecules almost visible under a microscope, and they still showed wave interference. Matter and light aren't just related by E=mc². They're ontologically the same kind of thing. They're both quantum objects that display wave-particle duality. The only difference is their energy configuration. Think about what this means for your body. Every particle in your body has an associated quantum wave function. You are, at some level, a wave. Not a metaphorical wave, but an actual quantum mechanical wave of probability spread out through space. The reason you seem localized, the reason you don't seem to be in multiple places at once, is because you're interacting constantly with your environment. These interactions cause what's called decoherence. They collapse your quantum wave function into a definite classical state. But in principle, you are a quantum object. Under the right conditions, if you could be perfectly isolated from all interactions, you would spread out like a wave. You would display quantum interference. The only reason this seems absurd is because you're so large and so hot and interacting with so many other particles that decoherence happens, essentially instantaneously. Some physicists, like the Nobel laureate Roger Penrose, have speculated that quantum effects might actually play a role in consciousness. The idea is that in certain structures in the brain, perhaps in microtubules inside neurons, quantum coherence might be maintained long enough to affect neural processing. This is highly controversial and not widely accepted, but it's a tantalizing possibility. Maybe consciousness itself is a quantum phenomenon, a deep expression of the wave-like nature of matter. Whether or not that's true, the fundamental point remains. You are made of quantum fields, configurations of trapped light, patterns of energy that have somehow achieved the complexity necessary for awareness. And this should fill you with wonder. Let's talk about another implication of all this, the vacuum. You probably think of vacuum as empty space, nothingness. But according to quantum field theory, there's no such thing as truly empty space. The vacuum is actually the lowest energy state of all the quantum fields that permeate the universe. But lowest energy doesn't mean zero energy. The quantum vacuum is seething with activity. Virtual particles are constantly popping into existence in particle-antiparticle pairs, existing briefly and then annihilating back into pure energy. This isn't speculation, it's been measured. One of the most precisely confirmed predictions in all of physics is the anomalous magnetic moment of the electron, and the calculation that matches experiment so precisely includes contributions from these virtual particles. The vacuum also has energy density. This is what we call vacuum energy or dark energy, and it's causing the expansion of the universe to accelerate. We don't fully understand it, but measurements from observations of distant supernovae show that the universe's expansion is speeding up, not slowing down. Something is pushing space apart, and the best explanation we have is that it's the energy of the vacuum itself. Think about that. Empty space has energy. A vacuum is not nothing. It's a something with structure, with energy, with the potential to create matter. In a very real sense, the vacuum is the substrate from which all matter emerges. Matter is just particularly stable excitations in this energetic vacuum. The philosopher and physicist John Wheeler had a beautiful way of thinking about this. He talked about quantum foam, the idea that at the smallest scales, space and time themselves are not smooth, but are constantly fluctuating, with microscopic black holes and wormholes forming and dissolving in the vacuum. This is speculative, but it captures something profound. Reality at its deepest level is not static. It's dynamic, energetic, creative. You exist in and are made of this dynamic reality. You're not in the universe like a marble is in a box. You're of the universe, made from it, continuous with it. Your existence is the universe doing one of the things it does, creating complex patterns of energy that can observe and reflect on themselves. Now let's address something you might be wondering. If matter is just trapped light, and E equals mc squared tells us about the equivalence of mass and energy, why don't we see matter spontaneously turning into light all around us? Why is matter stable? The answer has to do with conservation laws and quantum mechanics. While it's true that mass and energy are interchangeable, there are other quantities that must be conserved in any process. Things like electric charge, baryon number, lepton number. These quantum numbers can't just appear or disappear. They must be conserved. An electron can't just spontaneously turn into photons, because that would violate charge conservation. The electron is negatively charged, and photons are electrically neutral. An electron can only be annihilated if it encounters a positron, so that the total charge before, -1 + 1 = 0, equals the total charge after 0, if they produce photons. Similarly, a proton is extraordinarily stable because there's no lighter particle it can decay into while conserving baryon number. Baryon number is essentially the number of heavy particles, protons, and neutrons count as 1. Quarks count as 1/3. A proton has baryon number 1, and there's no lighter particle with baryon number 1, so the proton has nothing to decay into, though as I mentioned earlier, it probably does decay on extremely long timescales, which would mean baryon number isn't absolutely conserved, just very nearly conserved. These conservation laws are what give matter its stability. They're the rules that determine which transitions between energy configurations are allowed. Without them, matter would be incredibly unstable, constantly flickering between different forms. These laws are what allow trapped light to stay trapped long enough to form stars, planets, and people. But here's an interesting thought. These conservation laws themselves emerge from symmetries in the laws of physics. This is one of the most beautiful results in theoretical physics, called Noether's theorem, proven by Emmy Noether in 1915. Noether showed that every continuous symmetry in the laws of physics corresponds to a conservation law. For example, the fact that the laws of physics are the same at all times, that they don't change from one moment to the next, implies conservation of energy. The fact that the laws are the same at all locations in space implies conservation of momentum. The fact that the laws are the same regardless of your orientation implies conservation of angular momentum. So the stability of matter, the conservation laws that keep trapped light from immediately escaping, ultimately stem from symmetries in the fabric of reality itself. The universe has a certain elegance, a certain mathematical beauty, and that beauty is what allows complex structures like atoms and molecules and living beings to exist. This is why physicists get so excited about symmetry. It's not just aesthetics. Symmetries are the deep principles that govern what's possible and what's forbidden in nature. When we discover new symmetries, or when we find that symmetries are broken in certain ways, we learn something fundamental about the structure of reality. Let me give you another mind-bending perspective. We've talked about how matter is made of trapped light, energy frozen into stable configurations. But there's another way to think about this that's equally valid. Light is matter that escaped. Think about it. In the heart of the sun, nuclear fusion is occurring. Hydrogen nuclei are combining to form helium, and in the process, a tiny amount of mass is converted into energy. That energy is what we call light photons. Those photons, created deep in the sun's core, spend thousands of years bouncing around inside the sun before finally escaping into space as sunlight. When that sunlight hits your skin, you're feeling matter that was converted into light. Every photon from the sun was once part of a hydrogen nucleus. It was matter that got liberated, transformed into pure energy, and sent racing across space. And when you eat food and your body metabolizes it, converting chemical energy into the energy you need to live and move and think, you're taking advantage of the same process. The energy in your food ultimately came from sunlight, captured by plants through photosynthesis. Those plants converted light back into chemical bonds. You eat the plants or eat animals that ate plants, break those bonds, and use the energy. You're running on liberated matter. You're powered by light that was briefly trapped in chemical form. Every thought you have, every movement you make, every heartbeat, it's all powered by this cosmic cycle of matter becoming light and light becoming matter. This brings us to one of the most profound questions in cosmology. Where did all the matter in the universe come from in the first place? If matter and antimatter are created in equal amounts when energy converts to mass, and if matter and antimatter annihilate when they meet, why is there so much matter and so little antimatter in the universe today? This is called the baryon asymmetry problem, and it's one of the biggest unsolved mysteries in physics. In the early universe, when the temperature was high enough that photons had enough energy to create particle-antiparticle pairs, you'd expect equal amounts of matter and antimatter to be created. But if that were true, they all should have annihilated, leaving only photons. Yet here we are, made of matter, in a universe full of matter. Something must have happened in the early universe to create a slight asymmetry, a tiny excess of matter over antimatter. For every billion particle-antiparticle pairs that annihilated, there must have been one extra matter particle that survived. That 1 in a billion excess is what makes up all the matter in the universe today. All the stars, all the galaxies, all of us. We don't know for sure what created this asymmetry, but physicists have ideas. One possibility is that there are subtle differences in the way matter and antimatter behave, differences that would have been amplified in the extreme conditions of the early universe. We've observed some of these differences in particle physics experiments. Processes involving certain particles violate what's called CP symmetry, the symmetry between matter and antimatter. Another possibility involves the Higgs field. Some theories suggest that the Higgs field went through a phase transition in the early universe, and during this transition, quantum effects could have created the matter-antimatter asymmetry. Whatever the explanation, the fact remains: you exist because of a 1 in a billion imbalance in the early universe. You're made of the tiny excessive matter that didn't annihilate. In a sense, you shouldn't exist. The natural state would be a universe of pure radiation, with all matter and antimatter having annihilated. But somehow, the universe found a way to create and preserve a small amount of trapped light, and from that came everything we see. Now let's talk about black holes, because they represent the ultimate expression of the mass-energy equivalence we've been discussing. A black hole is what happens when you concentrate so much mass energy into such a small volume that the curvature of spacetime becomes infinite, or rather, becomes so extreme that nothing, not even light, can escape. But here's what's fascinating. According to Stephen Hawking's work in the 1970s, black holes aren't actually black. They emit radiation now called Hawking radiation. This radiation comes from quantum effects at the event horizon, the boundary of the black hole. Virtual particle pairs that normally pop into existence and annihilate in the vacuum can be separated at the event horizon. One particle falls into the black hole, the other escapes. The escaping particle is real radiation, and it carries energy away from the black hole. Over enormous timescales, a black hole will completely evaporate through this process, converting all of its mass back into radiation. The ultimate trapped light mass so concentrated it traps even itself, eventually becomes free light again. Everything that fell into the black hole, all that trapped energy, gets released back into the universe as photons. This raises deep questions about information and entropy, questions that physicists are still debating. When matter falls into a black hole, and then the black hole evaporates, does the information about that matter get destroyed? Quantum mechanics says information can't be destroyed, but general relativity seems to say it is. This paradox, the black hole information paradox, is one of the driving forces behind research into quantum gravity, the attempt to unite quantum mechanics and general relativity. But for our purposes, what's important is this: even in the most extreme gravitational environment possible, the interconversion of mass and energy continues. Black holes don't violate E equals mc squared. They're the ultimate demonstration of it. They show that mass is energy so concentrated, it curves spacetime to the breaking point. And energy is what you get back when that curvature relaxes. Think of a black hole as light that got so thoroughly trapped it created a prison of curved spacetime for itself. And Hawking radiation is that light gradually picking the lock and escaping, one photon at a time, over trillions of years. This idea that everything in the universe is fundamentally energy indifferent configurations has practical applications too. Nuclear power, both fission and fusion, works by converting tiny amounts of mass into energy. When a uranium nucleus splits, or when hydrogen nuclei fuse, the products weigh slightly less than the starting materials. That missing mass has been converted to energy according to E equals mc squared. The atomic bombs dropped on Hiroshima and Nagasaki converted less than a gram of mass into energy each. 1 gram, and look at the devastation they caused. This is the power contained in matter, the energy of trapped light waiting to be released. Nuclear fusion, the process that powers the sun and stars, is humanity's attempt to harness this power in a controlled way. If we can master fusion, we'll have access to nearly unlimited clean energy, because we'll be doing what stars do, converting matter into light. We'll be liberating the trapped energy in hydrogen atoms, turning matter into radiation that we can use to power our civilization. We're not there yet. Fusion is incredibly difficult to achieve in a controlled, sustained way on Earth, but we're getting closer. Experiments like ITER in France and the National Ignition Facility in the United States are making progress. Within your lifetime, we'll probably see the first fusion reactors producing more energy than they consume. When that happens, when we can routinely convert matter into light and harness that energy, we'll have achieved something profound. We'll be using our understanding of the fundamental nature of reality, the fact that matter is trapped light to power our world. Let me give you one more perspective that ties everything together. In quantum field theory, we talk about different types of particles, fermions and bosons. Fermions are matter particles, electrons, quarks, and so on. Bosons are force carriers, photons, gluons, W and Z bosons, gravitons, if they exist. But at the deepest level, this distinction isn't as clear as it seems. Supersymmetry, a theoretical framework that's been extensively studied but not yet confirmed, experimentally posits that every fermion has a bosonic partner and vice versa. Electrons have superpartner particles called selectrons. Photons have superpartner particles called photinos, and so on. In a supersymmetric universe, matter particles and force particles are intimately related, two sides of a deeper symmetry. We haven't found any evidence for these superpartner particles yet, which is disappointing for theorists who hoped supersymmetry would solve various problems in particle physics. But even if supersymmetry isn't realized in nature, the idea it represents is important. The distinction between matter and radiation, between fermions and bosons, might be superficial. At the deepest level, they might all be aspects of a more unified structure. String theory takes this even further. In string theory, all particles, both matter and force carriers, are vibrations of fundamental strings. An electron is a string vibrating in one pattern. A photon is a string vibrating in another pattern. There's no fundamental difference between them except the vibrational mode. If this is true, and again, we don't know yet if it is, then matter being trapped light isn't just an analogy or a consequence of E equals mc squared. It's the literal truth. Matter and light are the same thing, just vibrating differently. Imagine a guitar string. Pluck it one way, and you get a low note. Pluck it another way, and you get a high note. Same string, different vibrations, different sounds. That might be how reality works. One fundamental type of thing, strings or quantum fields or whatever turns out to be, at the bottom of it all vibrating in different ways to create all the particles and forces we observe. You are a symphony of vibrations. The particles that make you up are all playing different notes, creating a complex harmony that somehow produces consciousness, thought, emotion. Your music made from trapped light. Now, I want to address something important. Throughout this video, I've been talking about cutting-edge physics, about theories and ideas that are at the frontiers of our understanding. Some of what I've said is extremely well-established E equals mc squared, pair production, the standard model of particle physics. Other parts are more speculative string theory, certain aspects of quantum gravity, ideas about consciousness. It's important to distinguish between what we know with high confidence and what's still theoretical. The core idea that mass and energy are interchangeable, that matter can be created from light and light from matter, is rock solid. It's been tested in countless experiments. It's as well established as anything in science. The specific mechanisms exactly how mass emerges from the Higgs field, whether string theory is correct, how quantum mechanics and gravity ultimately unite, these are still areas of active research. We're still figuring out the details. But here's what's amazing. Even the established, confirmed parts of this story are so strange and beautiful that they should fundamentally change how you see the world. You don't need speculative theories to be awed by reality. The confirmed facts are mind-blowing enough. You are made of atoms. Those atoms are made of particles. Those particles get their mass from interactions with the Higgs field and from the energy of massless gluons. The energy in those particles has existed since the Big Bang. That energy can be converted to light, and light can be converted back to matter. This is the world we live in. This is the reality that science has revealed. And here's the thing, science isn't done. We're still discovering. The Large Hadron Collider might find new particles we haven't predicted. Gravitational wave detectors are opening a new window on the universe. Quantum computers might let us simulate quantum field theory in ways we can't today, revealing new insights. In your lifetime, we might answer some of the biggest questions. Is string theory correct? Is supersymmetry real? What is dark matter? What is dark energy? How do you unify quantum mechanics and gravity? These aren't abstract academic questions. They're questions about the fundamental nature of reality, about what matter and light and space-time really are at the deepest level. And you get to live in the era when we might find answers. You get to be alive during what might be the golden age of fundamental physics. How incredible is that? Let me bring this all back to you, to your life, to what this means personally. When you understand that you're made of trapped light, of energy that's been frozen into matter, several things should shift in your perspective. First, you should feel a sense of connection to everything else in the universe. The same fundamental stuff makes up you, the Earth, the stars, the distant galaxies. When you look up at the night sky, you're seeing your cosmic family. You're made of the same energy, governed by the same laws. Second, you should feel a sense of wonder at your own existence. Against all odds, in a universe that could have been filled with nothing but radiation, energy organized itself into atoms, molecules, cells, and eventually into conscious beings capable of understanding their own origins. You're one of the ways the universe has figured out how to look at itself. Third, you should feel a sense of responsibility. You're a temporary pattern in the cosmic energy flow. Eventually, the atoms that make you up will be redistributed. They'll become part of the earth, the air, the ocean. They'll be incorporated into other living things. The energy will persist, but your particular pattern won't. This means your time as this pattern, this configuration of trapped light, is precious. You have a limited time to experience, to learn, to contribute, to make your mark on the universe. Use it well. Make your pattern matter while it exists. Fourth, you should feel humble. You're not the center of the universe. You're not fundamentally different from anything else. You're made of the same stuff as rocks and stars. But you should also feel proud, because somehow, improbably wonderfully, this stuff organized itself in such a way that it can think about itself. You're the universe's way of understanding itself. That's extraordinary. Finally, you should feel curious. If reality is this strange, this beautiful, this unexpected at the fundamental level, what else don't we know? What other surprises await discovery? What will we learn next about the nature of existence? Stay curious. Keep asking questions. Keep learning. Because the story of matter and light, of energy and mass, of space-time and quantum fields, this story is still being written. And you're part of it. Every time you turn on a light, you're liberating photons, sending energy that was trapped in atoms on its way through space. Every time you eat food, you're harvesting energy that was captured from sunlight and temporarily frozen in chemical bonds. Every time you move, you're using energy that's been cycling through the universe for nearly 14 billion years. You are stardust contemplating stars. You are light that learned to trap itself and then learned to wonder about its own nature. You are a temporary ripple in the quantum fields that fill all of space, a brief flash of organized complexity in the cosmic story. And that's not diminishing. That's not depressing. That's glorious. Think about the journey your energy has taken. It emerged from the Big Bang as part of the primordial fireball. It existed as radiation for hundreds of thousands of years before matter formed. It became part of the first stars, was forged into heavier elements in stellar cores, was scattered into space by supernova. It coalesced into new stars and planets. It became part of Earth. It cycled through countless forms, rocks, water, air, living things, before eventually becoming part of you. And you're not the end of that journey. After you die, those atoms will continue. They'll become part of other things. In a very real sense, you're immortal, not as a pattern, but as energy. The fundamental stuff of which you're made has always existed and always will exist, just in different configurations. This is what physics reveals to us. Not cold equations and abstract theories, but a profound and beautiful truth about the nature of existence. Matter is trapped light. You are trapped light. And someday, you'll be free light again, racing through the cosmos at the speed of light, experiencing no time, no distance, just the eternal now of a photon's existence. But for now, while you're in this temporary configuration, while energy has organized itself into the pattern called you, appreciate it, marvel at it, because you're living proof that the universe can create meaning from meaninglessness, awareness from randomness, beauty from chaos. You're a miracle, a statistical miracle, an organizational miracle, but a miracle nonetheless. In a universe that tends toward disorder, toward equilibrium, toward the heat death, where all matter dissolves back into radiation, you're a temporary pocket of order, of complexity, of life. And you can understand this. That's perhaps the most miraculous part. Not just that you exist, but that you can comprehend your own existence, can trace your origins back to the Big Bang, can understand the quantum fields from which you emerge. You're the universe experiencing itself, yes, but more than that, you're the universe understanding itself. You're how the cosmos has achieved self-awareness. The trapped light that makes you up has organized itself so complexly that it can ponder the nature of trapped light. Let that sink in. Really let it sink in. The next time you look in a mirror, remember, you're seeing light that's been slowed down and frozen into matter. You're seeing frozen starlight, organized into a pattern that can look at itself and wonder. The next time you see sunlight, remember, that's matter that's been liberated. That's energy that escaped from the sun's core and is now free, racing through space, touching your skin, warming your face. The next time you eat, remember, you're consuming trapped light. You're taking advantage of the fact that energy can be frozen into matter and then released again. You're part of the cosmic cycle of trapping and liberation. And the next time you think, remember, your thoughts are patterns of electrical energy in your brain. They're ultimately quantum phenomena, configurations of energy flowing through neural networks. Your consciousness is the universe reflecting on itself, and that reflection is made possible because light learned to trap itself, and trapped light learned to process information, and information processing became complex enough to achieve awareness. You are extraordinary, not because you're separate from the universe, but precisely because you're not. You're an integral part of it, a natural expression of what happens when you let quantum fields evolve for 14 billion years in a universe with the right laws of physics. And here's the final, most important thing I want you to understand. This knowledge should empower you, not diminish you. Yes, you're just a temporary arrangement of atoms. Yes, those atoms are just energy configurations. Yes, that energy is ultimately no different from the energy in a rock or a star. But so what? That temporary arrangement is capable of love, of creativity, of understanding. That energy configuration can write poetry, compose music, prove mathematical theorems. Those atoms, organized just right, can experience the sublime beauty of a sunset, the joy of connection with another person, the satisfaction of solving a difficult problem. The fact that you're made of the same stuff as everything else doesn't make you less special. It makes everything else more special. It means the universe itself has the potential for consciousness, for awareness, for understanding. You're proof of that potential. You're what's possible when matter and energy organize themselves in the right way. So don't think of yourself as just atoms or just energy. Think of yourself as the universe at its most interesting, its most complex, its most aware. You're what 14 billion years of cosmic evolution has produced. You're the cutting edge of complexity in the universe, as far as we know. And that means you matter. Your choices matter. Your actions matter. Your thoughts and experiences and contributions to the world matter. Because you're not separate from the universe, you're how the universe acts. When you create something beautiful, the universe is creating something beautiful. When you learn something new, the universe is learning about itself. When you treat someone with kindness, the universe is expressing love. You're trapped light that learned to set other light free. You're frozen energy that learned to liberate more energy. You're matter that understood its own nature, and in understanding it, transcended it. So go forth with this knowledge. Look at the world with new eyes. See the light in everything, because it's literally there. See the energy flowing through all things, because it is. See yourself as part of the cosmic dance, because you are. You're not in the universe. You are the universe, temporarily organized into a pattern that can observe and reflect and understand. Make the most of it. While you exist in this configuration, while energy is trapped in the form called you, live fully, love deeply, learn constantly, contribute meaningfully. Because one day, your particular pattern will dissolve. The light will escape. The energy will be liberated. You'll rejoin the cosmic flow from which you emerged. But until then, you have the precious gift of existence, of awareness, of being. You are matter. You are light. You are energy. You are the universe, and you are miraculous. Thank you for taking this journey with me. Thank you for staying curious about the nature of reality. Thank you for being one of the ways the universe explores itself. If this video changed how you see the world, share it with someone else. Help spread the wonder. And remember, you're made of stardust, of trapped light, of frozen energy that somehow learned to ask questions about its own existence. That's not just physics, that's poetry. That's the most beautiful truth science has ever discovered. And it's true of you, right now, in this moment. You're living proof that matter is trapped light, and trapped light can be extraordinary. Until next time, keep wondering, keep questioning, and keep shining.